All right, let's begin. So welcome everyone, and thank you for joining today's webinar. We are really excited to show you what we have built in DYNAMIZU. This is our new advanced water treatment simulator. My name is Tanush Vadhavan. I'm a senior process engineer with Dynamita in North America. So this is our team. With Imri's vision, we have been able to build a new advanced water treatment simulator. And I want to acknowledge the whole team behind DYNAMIZU because it's years of work working with clients, gathering internal knowledge about water treatment to prepare the simulator. It's almost 45 years of continued innovation and vision of Imri, which has allowed us to do that. So today's webinar will be recorded and the recording will be shared. Please feel free to download and request a trial license and write to katie@dynamita.com for a license. If you have questions during the webinar, please feel free to put them in the chat. And we have teams standing by that will be able to respond right away. Or if some of the questions are missed, we will have the chat recording and then we can reach out to you personally and answer those questions. So that's one. The other thing is, although we have timed the webinar for 1 hour, even if it goes a little bit over, you feel free to stay or leave, but you will get the recording in completion. All right. So what are we going to talk about today? We are going to look at DYNAMIZU. So why we are developing DYNAMIZU, what DYNAMIZU is, and where it fits. And we are going to look at 3 different applications of DYNAMIZU. One is the breakpoint chlorination curve, which is very fundamental for looking at disinfection. The other is the reverse osmosis modeling application. And finally, we'll look at is an example of a reuse facility which is inspired from the Swift facility at Hampton Roads Sanitary District. So before we dive into the technical aspect, I want to mention the growth of reuse application in our industry. This is only potable reuse, which means that the wastewater is being treated and cleaned further using reuse application so that it can be used for drinking either now or in the future. So this does not include other non-potable reuse applications. So in 1960, there was the first plant which came out in California. And over the years, what we have seen is a tremendous growth of reuse application showing up in United States and all over the world. So by 2024, we had close to 25 plants that were doing reuse using their wastewater. In 2029, there'll be close to 45 plants which will be looking at doing reuse application. The green utilities which you see are in planning phase for the reuse application, while the purple ones are already under construction. So if I was to put this in some context, you will see that the number of facilities, number of reuse application facilities have grown from 1 in 1960 to almost, it's going to be close to 42 facilities by the end of 2039. So that's a significant growth. Now, as the industry is growing, we need the right tools which will allow engineers to design. We need right tools which allows the operators to understand and operate the facility. And this is where DYNAMIZU comes in. So Dynamita has been developing water modeling software for a while. Sumo, which you see on top, has the collection system, the urban watershed, along with very detailed, advanced modeling process units for wastewater treatment. The effluent of the wastewater treatment then can be used in DYNAMIZU, which you see at the bottom, in a combined ozonation treatment plant facility configuration, which you see, And that completes the cycle from wastewater to reuse. And this is where we are introducing our one water modeling solution. To give you a big picture, going from SUMO to DYNAMIZU, the purpose is to be able to treat wastewater to ultimately ultra pure water. So as you can see, I use 3 parameters: total organic carbon, turbidity, and TDS. From high strength wastewater to municipal strength wastewater, that is where SUMO comes in. And then as we go from wastewater to reuse application to pure water and ultimately ultra pure water, the water treatment requirements become stricter and stricter. And this is where it requires a new set of tools, new set of process units, new model which can handle those tricky situations. And that's where DYNAMIZU comes into play. Now, we have enabled SUMO and DYNAMIZU to be able to include in a digital twin package. So you can create process modeling automation applications, you can create digital twins using SUMO and DYNAMIZU. So you can send data in and get insight out of both SUMO and DYNAMIZU at the same time. You can send information from an open protocol communication, SCADA system, databases, .sumo file, a .mizu file which is the extension of DYNAMIZU. And you can send the data into the OPC, SCADA database, .sumo, and mizu files. And plus, we allow data exchange between SUMO and DYNAMIZU, which allows you to kind of evaluate the whole schematic of a treatment facility. So in order to distinguish what is difference between SUMO and DYNAMIZU, it's important to understand the biokinetic differences, the water quality differences, the process unit differences between the two. SUMO on the left is based on activated sludge models. We look at COD, we look at TSS, VSS, total nitrogen, total phosphorus. On the right, we have TOC, we have turbidity, TDS, salinity, hardness. Those are the important water quality parameters we want to focus on. Then comes the reactions that drive the model. We have microbiology-driven reactions on the left, chemistry and physics-driven reactions on the right. And then we have process units. In activated sludge models, we focus on aeration, clarifiers, digesters, dewatering units. And on the left-hand side, we are focusing on sand filters, membrane filters, ozone contactors, reverse osmosis, evaporators, and so on, right? So these are the major differences between the models. So we are shifting gears from activated sludge to water treatment. And finally, I want to mention that the 3 important water quality parameters such as TOC, BDOC, and turbidity, how they are calculated. So TOC, which is the total organic carbon, we focus on soluble, colloidal, particulate, organic carbon. And then there is a characterization tool which is available as part of the simulator. Then comes the BDOC. BDOC is the biodegradable dissolved organic carbon, and we keep track of that as well. And then there is turbidity, which is calculated based on the TSS and the colloidal fraction, which is in our wastewater, in our reuse water. So we keep track of those as well. The biokinetic model, which we call MIZU Pro, is a full plant water model. And in this full plant water model, our focus for the first release has been chlorination and disinfection. You can see that we have included breakpoint chlorination curve, which in itself includes 13 reactions. We focus on pathogen inactivation. We focus on coagulation and flocculation with polymer addition, with metal hydroxide formation, with pH impact, We look at emerging contaminants such as PFOA and PFOS. We look at it still includes some of the biological reactions such as hydrolysis, oxidation, BOD removal, denitrification, so that we can simulate biofilters. It still has two-step nitrification, denitrification process, sulfur oxidation process, and then it has precipitation reactions and some of the redox reactions as well, especially to mention the lime softening and hardness removal. So let's look at some of the process units which we have in DYNAMIZU. In DYNAMIZU, we have focused on membrane-based water treatment. So we have microfilters, ultrafilters, distinguishing between dead end and cross flow. We have reverse osmosis models, simple and advanced, membrane contractors, and EDI. We also have granular activated carbon, biologically activated carbon for TOC removal and TOC degradation. We have organic scavengers, ion exchangers, single bed and mixed bed application. And because water treatment is heavy on chemistry, it requires a lot of chemical dosing. So we distinguish between a big group of chemicals which we have. And finally, we have ozonation unit, a UV unit, and then air stripping and carbonator. So this brings us to doing our first application. So we are going to recreate the breakpoint chlorination curve. Now this curve helps us determine the chlorine dose required to satisfy the demand and achieve the free chlorine residual for pathogen removal, right, for disinfection. And what you see here on the x-axis is chlorine to ammonia ratio. As the chlorine dose increases, the total chlorine is increasing, and then it decreases, and when it rises back again, this is the free residual chlorine we are looking to have in our disinfection for a proper disinfection. And what you see at the bottom is the SKN, or the soluble caldehyde nitrogen, which includes the chloramines, which includes ammonia. And look at how it is being removed from the system as the chlorine dose is increasing, and ammonia. So we're going to recreate this curve in Sumo, or in DYNAMIZU. So I'm going to exit my screen, and I'm going to open DYNAMIZU. All right, this is DYNAMIZU. If you go to the home page, you will see that we have examples which are dedicated to reuse application, drinking water application, pure water application, and there are some other examples such as advanced RO with cleaning frequency, sand filtration, two-stage RO and evaporator, and finally there are some additional fundamental examples. So let's go to the Configure tab, and we are going to put together a simple configuration where we'll dose chlorine and look at different chloramines and total chlorine to reproduce that curve. So I'm going to go to reactors to start with, and I'm going to bring over a CSTR. I'm going to rename this to call this one chlorination tank. I'm going to go to the flow elements, and that's where I'm going to get the feed. Now you can see when I drag the feed over, on the left-hand side, we have many different source of water types. So right now, this is municipal effluent. We can choose to use river. So that's what I'm going to do in this example. So you can choose between different source types, and the difference is that the defaults are more relevant to the type of source water you choose. At the bottom, you can define the measurement either based on COD, either based on DOC or turbidity. So I'm going to leave other default settings. And I'm going to choose a dosage unit. So when I go to the dosage units, you'll see that we have a big list of dosage units, and I'm going to look for disinfection. So that's the disinfection. And I'm going to make this connection right here. I will go back to the flow elements and get treated water. Okay. One thing I want to mention is when you click on the dosage unit, you'll see that we have sodium hypochlorite. So that's what we're going to use. You can define the concentration of sodium hypochlorite in terms of stock solution and dosage type. So this is dosing point concentration. And this is very important because this unit allows you to define what the chlorine concentration is in the output port of this dose. And you don't have to figure out how much do you need to add to fix a particular concentration in the outgoing flow. And that makes it very easy for you to set this up. Okay, so that's what we choose. We're going to go to the models. And I'm going to make sure I save this file. And when I save this, you'll see that the extension is DYNAMIZU.mizu file. I'm going to just call it Breakpoint chlorination curve. You can see what I've selected is Mizu Pro. I'm going to turn pH on for this one because pH and temperature both are important for chlorination. We go to tools. We can decide to create a calculation in the tools. So I click on calculator, ratio of variables, and I'm going to say I'm going to create a calculation called chlorine over the ammonia. For this, I'm going to drag the dosage point to the numerator and then feed to the denominator. And then on the left-hand side, I can decide. First, I want to go to state variables. And then I want to choose free ammonia, free chlorine. So that's what I'm going to do. So that's free chlorine. And at the bottom, because it's feed, I want to define ammonia. So that's total ammonia. So now I've created a ratio of free chlorine to total ammonia. Okay. I'm going to go to the input and I'm going to define the flow rate at, let's say, 100 cubic meter per day. I'm going to click on my chlorination tank. But maybe in the feed, I want to make sure when I click on concentration of cations, I want to increase the ammonia concentration to 1 milligram nitrogen per liter. I'm going to go to the disinfection unit. I'm going to click on chlorine concentration based dosage, and I'm going to make this an advanced input into the model. Okay, so when I select this parameter will be available in the simulate tab, so I can make some changes. I'm going to go to chlorination tank, provide a residence time of about 30 minutes. So that's 2 cubic meter of tank volume. I'm just going to turn off the aeration by making the DO set point 0. And I think I'm ready to go. I'm going to go to the output. I'm going to start preparing some curves where I can simulate the total chlorine demand and in the species which are formed during that reaction. So I'm going to click on my chlorination tank. I'm going to create a time chart. All right. So in the output tab, I'm going to go to state variables, or I believe we can also go to other water quality parameters. So I'm going to click on other water quality parameters. You can see free chlorine is right there. So I'm going to get that. I'm going to get total chlorine. And I'm going to get some of these other species, which is available in the state variables. So I'm going to go to state variables and look for, okay, so a chlorination reaction will involve monochloramine formation. So let's look at that. It will form dichloramine formation and trichloramine formation. Okay, so that's what we're going to look at. On the same curve, I'm going to plot ammonia So that's something I will go back and find from frequently used variable. Not here. Maybe I'll go to the nitrogen components and get ammonia. Okay, so that's ammonia. I'm going to get the organic nitrogen as well, especially the soluble organic nitrogen. So I'm going to type in SKN. And I'm going to look for output soluble aldehyde nitrogen. And then I'm going to create one more time chart. Actually, two more time chart. The other time chart I'm going to create is TDS. So I'm going to go to frequently used variable. I'm going to grab total dissolved solids, because when you add chlorine, it adds to the total dissolved solids in the breakpoint chlorination example. So that's what we're going to do. I'm also going to add pH and alkalinity, because we are creating acid and that consumes alkalinity. So that's important to track. One more thing we want to add is dissolved nitrogen, because all of our constituents are going to convert into dissolved nitrogen. So that's when I'm going to create another chart. So state variable, I'm going to look for dissolved nitrogen. So that's what that is. And I'm going to just name this. So this is my chlorine and ammonia. Let's say this is TDS, pH related. And this is N2, okay, dissolved nitrogen. All right, so let's go and simulate. First thing I'm going to do is I'm going to go to simulate, and you can see that chlorine concentration based dose, which we chose in advanced, is now available right here. I'm going to increase the dose a little bit to 1 milligram chlorine, and I'm going to press start. Okay, you see some reactions coming in. But if we look for free chlorine, which is this blue line, you don't see it as part of any of these right here. So that means there is no free chlorine available. If you increase this, I'm going to increase the maximum here, and I'm going to add just a little more and press another dynamic simulation start. Okay, so now I see something coming up. This is dichloramine, monochloramine. That's total chlorine, right? So you see some, as you add chlorine, you see these increase. Okay, in DYNAMIZU, we have a feature where you can simulate a range of values. So I'm going to go from simulate on top to advanced. I'm going to choose to change the value of chlorine dose from 0 to 12, and I'm going to do 25 steady state simulations. So I'm going to change this to 25. And I'm going to press this steady state button. And I'm changing the value from 0 to 12. Okay. Now, remember that my ammonia was 1 milligram nitrogen per liter. So the ratio remains similar to that curve, which you saw on that slide. So I'm going to press steady state start. Oh, sorry, steady state. And this is where you see we are producing different constituents, right? So this green line is the total chlorine. And if I go back to my slide for a second, you see that this is the line I was trying to reproduce. This is the total chlorine dose, okay? Now, in DYNAMIZU26, what we also have is we also have a secondary y-axis, because the ammonia and SKN, or the soluble aldehyde nitrogen, is low concentration. I'm going to put it on a secondary axis. So I'm just going to click on this button, right? And I'm going to remove some of the intermediary compounds, right? So this yellow line is the soluble aldehyde nitrogen. This is what this is. You see that at the bottom of the slide. And now look at the ammonia. So you can see that the ammonia is being removed from the system. And what's being formed? I'm going to check on monochloramine. You can see that monochloramine rises, and then dichloramine, and then trichloramine. And this blue line right here is essentially your free chlorine, which is increasing. Okay. Let's look at what happens to TDS. By the way, if I didn't mention, my x-axis is no longer a time chart. It is no longer time, but it's chlorine concentration, because I'm doing 25 steady state calculations from a range of 0 to 12, and that's what this is. So these are 25 data points connected with each other, and we are creating an XY chart. I'm going to go to TDS and pH. Again, because pH is on a different magnitude, so I'm just going to put it on a secondary y-axis. That's alkalinity. I'm going to put pH. So you can see as we dose more and more chlorine, the pH starts to go down, and close to here, we are at 6.745. The alkalinity is consumed, and then you see that rise in TDS a little bit. That's the blue line, right? I'm going to show the nitrogen, dissolved nitrogen. You can see that dissolved nitrogen also increases a bit in this test. Okay, now let's go back to the input. The model we have is kinetic model. This model depends on the temperature and pH as well. So I'm going to go to pH and alkalinity. And I'm gonna, well, before I go to pH and alkalinity, I'm gonna go to feed specification, and I'm gonna increase the temperature to 25 degrees Celsius from 12 degrees Celsius, which is the river temperature in this case. I'm gonna go to simulate and redo this run, right? I'm gonna show you the impact of this curve. So if you notice, compared to the previous curve, the kinetics changed a bit, right? It became more favorable towards disinfection. If I go to input and now change the alkalinity to, let's say, 150 milligram per liter calcium carbonate in the influent, and if I go to simulate, remember in the previous, I spotted that the pH decreased to 6.7. So we're going to use that as a reference for our last value, 6.7. And I'm going to redo this run. All right. So let's look at the impact. Okay, it's a bit higher, 6.95 at this point because of the higher alkalinity. So the model we have is dependent on the tank volume size, which is the HRT, the dosage type, the pH, the amount of ammonia you have coming in with the feed, and so on. Okay, and it affects TDS, it affects pH, it affects alkalinity consumption, it affects nitrogen gas being generated, right? So now let's do one last exercise. I'm going to go back to the input. I'm going to make the ammonia concentration 10 times. So I'm going to increase the ammonia concentration from 1 milligram nitrogen per liter to 10. I'm going to go to the simulate, and I'm going to redo this run. Okay, keeping my range of chlorine dose the same. Well, as you can imagine, of course, there is no free ammonia at this point because we are dosing a lot less than what is required. So I'm going to increase the range right here. So I'm going to say, instead of 12, add 120, right, at the end, and keep the same 25 simulations. So that means now my ratio is back to what it should be. And I'm going to do steady state again. And what I should expect is a similar curve. So you see, green line is total chlorine. You have that theoretical drop, and then increase because of free ammonia simulation. Let's look at TDS, pH, and alkalinity. Okay, a lot more drop in pH, and then a lot more increase in TDS. So if you're working with pure water or ultra pure water, this is an important thing to keep in mind, right? Because TDS increase is not something which you might be looking for, but maybe for a drinking water application, it's fine. Look at the consumption of alkalinity, and let's look at nitrogen gas, dissolved nitrogen gas, right? And that significantly increases as well. So this shows you the dynamics, the kinetics behind the model. It's very fundamental to what we want to do. Okay, I'm going to save this, and I'm going to go back to home, and I'm going to open a new project so that I have a new file. And I'm going to go back to my slide here and see what we have, what's the next thing we want to talk about. All right. So the next thing we want to talk about is reverse osmosis modeling. Okay. And what you see on this slide is on the right axis, I have summarized a set of simulations I did with our advanced RO model where I maintained the feed constant. I adjusted the feed flow to maintain the permeate flow or the produced water while I'm adjusting the recovery ratio, because I wanted to show the impact of recovery rate on the feed pressure, on the flux of the whole system, right? So the impact of RO and many different operational conditions can be simulated using this model. So we're going to try to put together a simple model right here, okay? So I'm going to go back to DYNAMIZU and let me see if, okay, this is the other file. Okay, I'm going to open a new file. I'm going to go to configure and I'm going to look for RO. RO is available in membranes. So I'm going to go to membranes and I'm going to go through and say, okay, this is the advanced RO I'm looking for. I'm going to go to the feed flow. This time I'm going to keep the municipal effluent source water. I want to add a pH control because, as you'll see in a moment, that pH control is very important for RO. I'm going to go to the dosage units. And in dosage units, you'll find we have an inline pH control. And this, you'll see, is a very important unit to have in drinking water because there can be pH controls all over the place. We don't want to put individual controllers together, but you can put an inline controller and just set the pH. And the model will tell you what is the amount of caustic or sulfuric acid is required to meet that set point. And then it's also including that volume in cost calculation as well. Okay. I'm going to go to flow elements and I'm going to get treated water, which is our permeate. So I'm going to rename this to permeate. I'm going to get on the left-hand side, I'm going to get the concentrate discharge. And I'm going to get concentrate discharge as well for the cleaning waste. All right. Now, why is it important to choose this one? Because on the left-hand side, you see, we allow users to define what type of waste this is. And that's important because there are cost implications when you are, especially if you're looking at pure water or if you're looking at ultra pure water facilities, right? So I'm going to change this to cleaning waste, and appropriate cost of the waste will be calculated as part of this model, okay? I'm going to make sure at this point I do a save as. I'm going to call it RO and just save it on my desktop. I'm going to click on Advanced RO and show you some of these important settings we have. So right now I'm using a continuous operation RO, but it is possible to simulate the dynamics, the cyclic ability of an RO and proper backwash cycle. So you can reproduce the exact operation of your RO in terms of in terms of water flow. Then you can decide how you want to operate. So I'm going to let the set recovery ratio be our default model. You can decide to choose the pressure as set as well. You can change the number of stages. So right now, this is a 3-stage RO, as you can see, the 3 stages. You can use 1-stage RO, and this is the 1-stage RO, and build your 3-stage RO if you want. But you can imagine if you build a 3-stage RO model out of this one unit, then you have to make sure that the recovery ratio is set for the total system, right? This 3 stages allow us to kind of set that as a one input into the model. So it's a simplification. Very good. It's not a simplification, but it's a very good model for you to set so that you don't have to worry about how to set it up, right? You can define the brine's recirculation. I'm going to choose specified fraction of brine. You can see that we have a slew of cleaning solutions and in low pH and high pH, depending on scaling you're looking at. One important thing I want to mention at this point is that we have a very strong energy and cost model. So I'm going to double click on this energy mode. on top of my drawing board. You can see if I click on my RO now, then we have option of defining what the pump curve will look like. Will it be an empirical pump curve for RO, or will it be a high pressure centrifugal pump, right? And then you can add your pump curve if you wanted to this RO. Okay, I'm gonna leave it at that at the moment. And I'm gonna go to model setup. In the model, I'm gonna choose to calculate pH, because pH is important for RO. I'm gonna go directly to the input. In the input, I'm gonna click on the feed. So you can see that this is still a COD-based unit. I will define the flow rate. So I'm gonna make the flow rate to 1000 cubic meter per day. I'm gonna click on the inline pH control and turn the pH off to start with. I'm gonna turn it off by typing in a 0. I'm gonna click on my advanced arrow to show some of the model options we have. You can define number of trains, you can define number of pressure vessels per stage. So each stage can be defined. And then in each stage, you can define different elements based on the specification of design. On the left-hand side, if I change this, the option, you can select the membrane surface area per element. You can decide the design net driving pressure and permeability of new membrane. So when we are looking at water flux, we are looking at feed pressure, we are looking at permeability, we are looking at recovery ratio. So all of those are included as part of this model. We are looking at osmotic pressure, right? Those are part of this model. And if I go to the RO operation, then this is where you can define the recovery ratio, okay? So I'm gonna choose the recovery ratio of this model as an advanced variable, so I can look at how I can do some sensitivity analysis, let's say, okay? I'm gonna go to the output. I'm gonna create a time chart. And what do I want in my first time chart? I'm gonna look at flow rate in permeate and my concentrate discharge. So I'm gonna click on permeate, go to flow, grab my flow rate. I'm gonna do the same thing for the brine. Well, I wanted to rename this to brine. So that's what this is. And this is my cleaning waste. All right, so that's my brine. It's easier to follow. On the other chart, so this is, let's say, my flow. I'm gonna create another chart where I'm gonna put in the brine concentration. So I'm gonna click on frequently used variable, and I'm gonna look for turbidity. Okay, I also have electrical conductivity, hardness, salinity, all the important water quality parameters. TDS, this is what I'm looking for, okay? Now, what else is important for RO is scaling potential. So we can predict scaling potential. I'm not gonna show you all the scaling indices which we follow, but I'm gonna show you a total sum where it says either it's scaling or how many scalants are possible in this operation. So I'm gonna look for something called deposit. So we have a deposit flag, and these are some of the scalants, but I'm gonna choose deposit flag to follow. All right, so this is our TDS. I'm gonna create another chart where I'm gonna show pH and its effect, okay? So I'm gonna click on my permeate. I'm gonna go to my pH and drag my pH to the right. And then I want to point out the importance of pH on, let's say, free ammonia in the effluent or in the permeate, or carbonic acid in the permeate, because the rejection depends on pH of and pH changes the species of these individual components, right? So I'm going to go back to permeate. I'm going to click on other variables, equilibrium species, and you can see that we have a lot of equilibrium species which we use for pH calculation. I'm going to grade just the free ammonia. and I'm going to get just the carbonic acid, okay? And finally, I want to put in my pressure and pumping cost. So I'm going to click on my advanced arrow. I can look at fluxes, different pressures. So I'm going to go to pressure and I'm going to say feed pressure. I'm going to go to power requirement and I'm going to drag process unit, electrical power demand. I'm going to go back to simulate. And this is where I'm going to do that simulation, okay? So I'm going to dive directly into doing the analysis. I'm going to analyze steady state between 60% and 90% of recovery. And I'm going to do 10 simulations, 10 steady state simulations, okay? I'm going to go back to the flow and press this steady state. So what do we expect? As the recovery ratio is increasing, our permeate flow is increasing, right? And our brine flow is coming down. Now, when our brine flow is coming down, what should we expect in terms of TDS? We should expect our TDS to increase. So that is our TDS, okay? So our total dissolved solids is increasing as our recovery ratio is increasing. And I'm going to put the deposit flag on the secondary y-axis. So you can see, okay, when you are operating at low recovery ratio, there is no scale length, zero scale lengths. If we go beyond this 73% threshold, we get 2 scale lengths. And if we go further up, you can see that we get 3 scale lengths, right? So as the brine is getting more and more concentrated, we are able to see that impacts the operation of the plant. If we go to the pH, and again, I'm going to put pH, I'm going to put, let's say, carbonic acid on a secondary axis first. And then you can see as the pH is going up, in the permeate, you can also see that the carbonic acid concentration is going up as well, right? If I look at free ammonia, as the pH is going up, the free ammonia concentration is also going up. Okay. And finally, the pressure and impact on our pumping. So as the brine recirculation is happening, more concentrated TDS is coming back, our pressure is increasing, and so is our pumping cost. Okay, so this is evident, right? Now here we are doing an analysis of a system, and we can identify important points which we might miss from a Excel file or hand calculation. So we are able to put together a full-scale facility and kind of be able to evaluate the impact, right? Now, what is important for a RO operation? Keeping the flow constant. In a municipal setting, okay, keeping the flow constant might be possible, but it changes the characteristics such as COD, it changes pH, the temperature might be changing. So we can do one quick simulation with and without turning on the pH and look at the impact on the dynamics of the system. So I'm going to go back to the input and I'm going to add a dynamic table to the feed. And I have the table prepared in this Excel file, changing the pH. The pH is in the beginning is 6.7. It increases to 8 and then it comes back down to 6.7. The temperature during that 1 month period is increasing from 15 degrees Celsius to 30 degrees Celsius or 25, 24 degrees Celsius, right? Now, this is a municipal application. In water, in ultra pure water settings or pure water settings, it's possible that I have to click on feed. It is possible that the temperature is being controlled, right? Okay, I'm going to click on my pH control, and I'm going to select that as an advanced variable in the advanced settings. I'm going to go to simulate. And this time I'm just going to do a dynamic simulation of 30 days. Okay. And I'm going to do two scenarios. One, with 90% recovery. Okay. One where the pH is off, and the other where the pH is on. Okay. All right. So we are doing 90% recovery. You can see that the flow rate is 900 cubic meter per day. The flow rate is not changing because the recovery ratio is set. The flow rate is constant. If you look at our TDS, at the moment our TDS is constant, and we have a deposit flag of 3 scalens. And you can see as the dynamic table kicks in, right? The temperature is changing, the pH is changing. The deposit flag shows that at higher pH, you have 2 scalens and not 3. If we keep track of our pH, you can see this blue line is our pH in the permeate going up. And as the pH goes up, our free ammonia concentration increases and our carbonic acid decreases. And then finally, if we look at our pressure and pumping cost, you can see as the temperature is increasing towards the end of this simulation, the feed pressure is going down. And that, of course, has an impact on our pumping cost. The second simulation already started. You can see in this case, we are controlling the pH. So if I go back to the pH curve, you'll see that this blue line, which is coming up right now, will not allow you to, will not go back up to this 9.4 pH in the permeate, but it's going to stay relatively constant. And that's important to know. Okay. Now, this means that there is no longer that free ammonia which is leaking through, and that has impact on the carbonic acid as well. If we go to the feed pressure and pumping cost, it didn't change much for the RO. And if you look at TDS, of course, TDS is impacted because we are adding caustic upfront, right? But in this case, it did not have much impact on deposit. The deposit. Okay, so this was one set of simulation which I wanted to show for RO. All right, so I'm going to save this, and I'm going to go to my last set of simulation. Okay, so for the last example, we're going to look at a reuse facility, and you can refer to this paper on top by Hogarth, and this paper describes a case study of the Swift facility by HRSD, the Hampton Road Sanitary District. They take wastewater from the enhancement treatment plant, effluent goes into a coagulation, flocculation, sedimentation tank with some chemical addition, polymer addition. Then it goes through an ozone contactor into their biofiltration where they remove TOC. Then it goes through a GAC, which is granular activated carbon, UV, and then it's ready for aquifer discharge. Okay, and this model will show you that you can really use Sumo for doing a sizing design, and you can, or DYNAMIZU. Let me correct. So we can use DYNAMIZU for doing the sizing. We can use DYNAMIZU for optimizing the operation of the facility, right? So what are we going to first reproduce? We're going to reproduce the TOC curve, or the total organic carbon curve, which they observe. So in the influent or in the effluent of their facility from wastewater, they have TOC ranging from 8 milligram per liter of carbon to close to 12 milligram. And then they have about 30% removal after their flocculation sedimentation tank, then another 20-30% removal in their BAF and GAC and so on. So GAC is ultimately the barrier which prevents TOC from going out, right? Because it absorbs organic carbon. But its operation can also depend on the carbon load which is flowing through the system, right? If one of these systems, if you have a lot more carbon coming in, if you don't have your sedimentation tank performing properly, then of course GAC will be impacted. And GAC is very important to maintain because, you know, it takes it takes money, it takes time to kind of replace the amount of organic granular activated carbon we have in that system, right? So that's what we're going to do. So I'm going to go back to DYNAMIZU. I'm going to go to my home page and I'm going to open this first example, which is the reuse example. Okay. If I click on my feed, this is municipal effluent with dissolved organic carbon defined. I'm adding pack with some pH control, and I'm gonna just make this a bit bigger. Coagulation, flocculation tank, sedimentation, followed by ozonation, reactive filters, granular activated carbon, feed tank, and granular activated carbon, UV reactor, and some chlorine dose at the end, right? Let me go to the input. And one thing I want to mention in the model is if I go down, you can see that in order for you to look at, let's say, PFAS or pathogens, you have to activate that selection option. So this is where we selected pathogens. I'm going to go to the input. In the input, one thing I want to mention is that if you're familiar with wastewater modeling, you have to characterize your influent. And in Sumo, we have had this tool for influent fractionation. We have a similar tool available as part of this DYNAMIZU as well, where you can characterize based on DOC or TOC appropriate fractions for this model. Okay, let's go to the output. And simply, I'm going to create first a bar chart so I can show you how it looks similar to the data we have in that slide. So I'm going to rename this to SCE. So that's the effluent facility or effluent from the facility. I'm going to go to frequently used variable and then look for TOC. I'm going to grab TOC from the sedimentation effluent. I'm going to grab it from the reactor filter, and I'm going to grab it from the gap and the discharge, aquifer discharge. Okay. So now you can see that we're going from 8 milligram carbon per liter to 6.5 to 1.6, and then we are getting into a low range. And that's what we see right here happening, right? That's what we can reproduce. If you look at, we can look at the performance of the filter, we can look at the performance of the chlorination, how much free chlorine is available. We can look at pathogen inactivation, so E. coli and cryptosporidium. We can look at power demand. We can look at cost associated with the operation. And let's look at BDOC. As we know in this system, what's important is that ozonation converts some of the refractory compounds and makes it biodegradable. And that's what we keep track of. So I'm going to track BDOC. I'm just going to make sure 0.3 milligram carbon per liter going in and then 4.8 coming out. So that means biodegradable organic carbon is being generated after ozonation, right? So, and that's important to keep in mind. Now, we want to click on GAC. And I want to show you one dynamic simulation in this facility, okay? So for that, like I mentioned, GAC operation is very important. So what I'm going to do is, I'm going to go back to configure. I'm going to change the type of GAC model we have. So we have continuous GAC model, but I'm going to change it to cyclic, make it a little more advanced. So we can simulate the backwash cycle and we can simulate the consumption of the activated carbon, or at least the replacement of the activated carbon. And I'm going to choose the breakthrough-based total absorbed carbon. I'm going to simplify for the time's sake. I'm going to turn off the energy and I'm going to go to the input. So while the model is recompiling and getting ready, I'm going to click on the secondary effluent. I'm going to increase the load to the plant. So instead of 4,000 cubic meter per day, I'm going to make it 6,000. And then instead of only 6 milligram of carbon per liter, I'm going to make it 15 milligram carbon per liter of as dissolved organic carbon. Like I mentioned, when we change the total, the fractions are also impacted. I'm just going to reduce the fraction of nitrogen which is associated with the carbon. So I'm going to make that really low, 0.1, so it doesn't make the state variables negative. And you can see it already compiled. What I'll go do also is go back to the input, click on the gap, and I'm going to reduce the adsorption capacity of the carbon. So I'm going to say that the carbon which came in, granular activated carbon, is not that good. I'm going to go to the operational, and plus I'm going to add more TOC load. And I'm going to go to this operation and replacement cycle, and I'm going to say that the duration of bed replacement, so the time it takes for the operators to replace the organic, the granular activated carbon after there is a TOC breakthrough, is 48 hours. So I'm going to change that to 48 hours. Okay. I'm going to go to output, and I'm going to keep track of two things. I'm going to create a time chart, go to operational, and drag number of beds being replaced and the cumulated mass of activated carbon. Okay. And I'm going to put that on the number of beds on the y-axis, secondary y-axis. I'm going to do this. I'm going to get the TOC from the effluent and plot that on another time chart. All right. I'm going to go to simulate and change this to 15 days. Do a 15-day simulation. And I'm going to do a 10 minutes data interval. And I wanted to change the backwash cycle to 30 minutes. Okay. All right. I'm going to go to simulate and press start. So now you will see that there is a little bit of dynamics associated with the granular activated carbon. So you can see during the backwash, the flow just goes through. In a facility, if you can have multiple granular activated carbons. So if one is operational, the other one is inactive, in a backwash cycle, you can put two, similar to how you'll put together an SVR. To capture the dynamics of the system, you can put two in parallel and then operate it based on the backwash cycle. Okay. So what you see is during the backwash cycle, the TOC is increasing. And what I expect you to basically see is in a moment. And if I have the number of beds right here, okay, so you can see the number of beds replaced in granular activated carbon is 1. So over 15-day period, there was 1 cycle of replacement which happened. That impacted the TOC. You can see your TOC going up, and that's when the replacement started. It took 48 hours to replace that all granular activated carbon. And then when it was replaced, it went back to doing what it does. So you're able to keep track of the mass of granular activated carbon you have removed, the number of times you have removed. And if you go to the cost, you're able to see the replacement cost. So that's 50,000 USD for that 15 days of operation, right? So that's a little bit of dynamics. Okay. All right. So just few minutes and then we will stop. I just want to highlight some of the important key points. With the breakpoint curve, pH, temperature, and kinetics impact the breakpoint and residual. Chlorination increases TDS and consumes alkalinity. Okay. Sorry, I had a timer set for myself. Reverse osmosis, we saw the impact of recovery ratio on the RO performance. Temperature affects flux. pH control is important. In the reuse facility, we saw the TOC being removed, turbidity being removed. Ozonation can increase BDOC. The GAC performance is important for low TOC and low turbidity, right? That's what we saw. Okay, so finally, we are pushing the water modeling forward, right? We are working hard to introduce water technology models which are relevant, which have variables which people want to use, engineers and operators, and we have appropriate defaults. It can be used for design, application, and operation, and integrated into digital twin workflow, right? Now, what's next? We are in the next release, we are going to look at ozonation in more detail. Right now, it's just a process unit. We are going to look at disinfection byproducts in more detail. So bromate, bromide, other organic disinfection byproducts, and nitrogen disinfectant byproducts. We're going to look at pathogens. We're going to look at emerging contaminants and metal recovery removal chemistry. Okay. Now, with that, I would like to thank everyone